Section 4.2 is titled Area. And what we're going to look at this section is actually taking a curve and finding the area underneath it. Before we can do that, we need a little bit of notation and language. So the first piece of information we're going to talk about is called sigma notation. The sum of the first n terms, a1, a2, a3, all the way up to an, is written as the sigma from I equal 1 underneath it up to n of a sub I. And that is just a1 plus a2 plus all the way up to an. I is called the index of the summation. A sub I is the ith term. And the upper bound is n, the lower bound is 1. So we're going to become a little familiar with this notation before we jump into the area stuff we're going to do in a minute. All right, so we're going to do an example for how this actually works, this process, what this looks like. This says to find the sum, and the summation is from I equal 1 to 6 of 3i minus 2. All right, so what this notation means is I'm supposed to find the first 6 terms. How do I know it's 6? Because it says I start with 1 and I end at 6. Okay, so I'm doing the first 6 terms. So what I want is I want to take a1 plus a2 plus a3 plus a4 plus a5 plus a6. I mean, that's what I'm wanting to do, and I'm wanting to add them together. Now, of course, right now, I don't know what those values are. They aren't written down anywhere for me. So the way that I find them is I use the equation that I'm given right here, and I find out what is a1. So a1 simply means taking the number 1 and plugging it in for the letter, in this case I. And this is not I like complex numbers or something like that. This is I, as they use I for the word iterated. It's an iterated sum. It continues to go up. So sometimes you'll see used I. Sometimes they'll use a J or a K here too, just so you know. So this is taking the 3 times 1 minus 2, and we're just finding out what is a1. So what would a1 be here? 1. Right? Okay, so a2, I do the same thing. 3 times 2 minus 2. What does that give me? 4. How about a3? 7. How about a4? Does anybody notice a pattern? They're increasing by 3 every time, and of course the reason for that happening is because of the 3 right there. This is what we call an arithmetic sequence. You may have seen that in an algebra class somewhere in the past. So a5, without even writing this down, should be the number what? 13, because it should be 3 more, and a6 would be the number 16. So at some point, if you do happen to notice a pattern, you're welcome to use that pattern to generalize the next 2 values. And what we're wanting to do then is we're wanting to add these together. So we have 1 plus 4 plus 7 plus 10 plus 13 plus 16. And if I add these together, 51. Okay, any questions on that? It's not hard, right? You're just using a little bit of algebra. There's no calculus involved in what we just did. It's just a little bit of algebra to evaluate, and then you're summing in them at the end. Yes, and we're going to do an example where it's going to start somewhere else in a minute so you can see how that affects things. But you're exactly right. The fact that this says I equals 1. Let me change that. That was too thick of a pen. The fact that this says I equal 1 tells me I start at 1. So if this said I equal 3 to 6, then we wouldn't have I1 or A sub 1 or A sub 2 in there. We would start with A sub 3. Does everybody catch that? And we are going to see that happen in a slightly different context in a moment. All right, so this works fine if we added up 6 terms. I don't know about you, but if they wanted me to add up 30 terms doing this, that would not seem so fine, right? It would seem to be just kind of a waste of my time. And so what we're going to show you next is I'm going to show you that there are some shortcuts to actually doing summations for these that prove quite helpful when you have larger numbers of things you're trying to add together. If you're doing small numbers of things, this is fine, and this is probably faster even than using what I'm about to show you. But for larger numbers of things, generalization patterns are helpful. So there are four summation formulas that I'm going to show you. The first one says if you take the number C is a number here, it's a constant, and you add it together so many times, you guys know what that's going to give you, right? So if we had I equal 1 to 6 and I had the number C 6 times, what would that be? C equals C equals C equals C. How can I write that shorthand? 6C. So what I have here is I have whatever the constant is I'm supposed to be adding these multiple times times the number n. This is called a sum of constants. Okay, you have a whole bunch of constants, you're just adding a whole bunch of constants together. Well, a fancier way of doing that is called multiplication. You multiply the number of constants you have times the constant value. All right, sorry, go ahead.
If I is different though, other than 1, will that not work?
It will work, but you have to do a small change to it, and I'm going to show you how to do it in a minute. But I'm glad that you're mentioning this, Evan, because it's definitely an omission that I get a lot of times, is that all of these formulas are set up to start at I equal 1. So if I does not start at 1, you do have an extra step you have to do on the end of it, and I'll show you what it is, to fix the fact that it didn't start at the right value. Okay? Same thing's true if I started at 0. I mean, could we have I equals 0 as our starting spot? Well, sure we could. But these summation formulas only start at I equal 1. So these summation formulas have to be used specifically for 1 to whatever your capped value is. Okay? All right. Promise I'm going to get there. I promise. All right? The next one is adding the numbers together that are the numbers themselves. So if you have I equal 1 to n of I, and then you're going to be adding the numbers together of 1 plus 2 plus 3 plus 4 plus 5, all the way up to wherever your n value is, right? Are you guys with me? I'm going to show you how we derive this one because I find it to be a very simple one to show you. It's also intuitively nice. So let's say, for instance, we have the first, and I'll just do the first 100 of them. 1 plus 2 plus 3. And we're going to go all the way up to 100. So 98, 99, and 100. Okay, so this would be the summation of number 2 here, where I goes from 1 to 100. Are you guys with me? We'd like to find a formula so that I don't actually literally have to sit down and write all this down and add this up, right? That does not look like a fun thing to do. So what we're going to do is we're going to do something a little bit funny. We're going to add this to itself, but in reverse order. So I'm going to put a 100 here, 99, and 98. All the same numbers as before, just backwards. And we're going to add them together. Okay, so this is a big old giant summation. So I have 2s on the left. Everybody with me so far? I know you don't know where I'm headed, but are you with me so far? Okay. We're going to add them up in pairs straight down like this. And what do you notice when you start doing that? They're all 101. Whole bunch of 101s, right? They're all 101. Because we added them up in that way. I mean, we did it on purpose to do that. How many of them are there? There's 100 of these. Right? Because we started at 1, we ended at 100. There's 100 of them, right? So what is a shortcut way of writing 101 plus 101 plus 100 times? 101 times 100, right? So far, so good? I don't really want to know what 2s is, though. I want to know what s is. So my s value is 101 times 100 divided by 2. What's wrong? Yeah, that's true. It is 5,050. I'm not really concerned about the total value. Remember, my goal in showing you this is I wanted to show you where the formula that I'm about to show you is that it came from. So take a look at the number 100. Where did the 100 come from? N. It was the top N value that I picked, right? I just arbitrarily picked it. So my formula over here is going to take the number N. And then how do you think the 101 is related to the 100?
N plus 1.
It is N plus 1. That's right. And the denominator really is 2. And this works for any sets of numbers, right? And this is was actually developed, you're going to love this, by a 6-year-old mathematician. He was 6. Do you know his name? Gauss is his name. And basically what happened was that he had a first grade-ish teacher who said, I want you to, I'm guessing it was first grade, based on the fact that he was 6. Yes, the teacher needed a break. The teacher told the students, I want you to add the numbers up from 1 to 100 and tell me what you get, which should take a while, right? And it did not take him a while because he figured out a pattern and he used this pattern to solve that problem. So we can all feel highly inadequate that a 6-year-old could do that, right? I know. All right, so this is the one, this is Gauss's theorem. All right, so we have a couple others. I'm not going to justify these for you. There are more justifications in your book if you're interested. The next one is the sum of the squares. So this would be like having, 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, like that together. You do have, it looks similar to the last one. You have n times n plus 1. That part's the same. And then you have 2n plus 1, and it's all over 6. And then the last one is the sum of the cubes, right? So like 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed, and so forth. This is n squared times n plus 1 squared over 4. Which should look an awful lot like this one right here, squared. Doesn't it? Yeah, it is. Okay, so now I'm going to show you how we actually use these. Okay, you guys ready? Okay, flip to the next page. You've got a summation. This is only from 1 to 16. If you wanted to do this by hand, could you? Sure. I mean, you could. It's only got 16 values you're going to evaluate. You're going to add things together. It really wouldn't be that bad, okay? But we're going to do this with the summation rules because that's the directions for it and because I want to show you how they work. Now, you need to be careful because this 5i minus 4 does not look specifically as it is written right now like any of the rules, right? But we have an ability with summations, much like we had when we had limits and derivatives, of being able to separate pieces apart. So what I'm going to do is I'm going to separate the pieces that I can. This 5 in the front here can come to the front. It's a coefficient. It doesn't get mixed up in all that's going on. It really doesn't. It's just going to be multiplied at the end. I'm going from I equal 1 to 16. And the next value I have is the I. Now, the fact that this is subtracted means that I can also separate that apart. So I can subtract and I can do another summation from I equal 1 to 16 of negative 4. Well, of 4 because I used the negative already. You could put plus a negative 4 or just minus the 4 there. I don't know why that didn't rewrite. This is my problem. This is why my iPad's been being looked at. That's better. Okay, did I get everything in there right? Does it look okay? Now, each of the summations that we actually ended up with here and here have the form of something on the previous page. Okay? So again, the 5 here in the front is just going to stay. But the value right here is the summation value for I. It's the second rule, right? The second property of summations over here. Except for the n value that we have is not just n, it's actually 16. So we're going to use that rule with 16 plugged in. So this is 16 times 17 divided by 2 minus. Now, and this would be 4 times the 16, right? This is the first rule. It's a constant, like the c, times the number of terms, 16. So grab your calculator, simplify, tell me what you get. Six, 16. Okay? Everybody's good with the fact that this is not calculus, right? We're going to apply these concepts to calculus in a moment. So far, this is algebra. All right, Evan, where does this one start? At 4. This is the one I was talking about. Okay, so our properties on the previous slide, 2 slides ago now, don't start at 4. They start at 1, right? So in order to use them, I need my summation to start at 1. So I'm really going to change this summation, really and truly, to start at 1. I'm going to go ahead and multiply this out too. This is n squared minus n. But you can't just change things, right? You can't just like get rid of fractions, and you can't just, like ignore pieces of an equation that you don't like. You have to compensate for them, right? If you change something somewhere, you're probably going to have to change something somewhere else. So what did I do by changing this from n equal 4 to n equal 1 as my starting point? What did I really do? I added 3 more terms. I added a1, a2, a3, correct? So if I added them in right there, what do you think I'm going to do? I'm going to subtract them off at the end. So this is minus a1, minus a2, and minus a3. That's my compensation. I added them in by starting at n equal to 1 on the lower part of the summation. I subtracted them off at the end. So I will have to calculate those values independently in the equation to do that. You could, but there's only 3 of them, so it's not terrible. Yes. Mm-hmm. Yeah, that's a good point. So like let's say this started at n equal to 40 instead. Sure. Then we could do the summation at the end here, and this piece right here would say the summation from I equal 1 to 39 that I was removing, right? Absolutely. Yeah, good question. Okay, I'm going to erase that part of it since it didn't say that. I don't want you guys to look back later and be like, why is there a 40 in the problem? The other thing that I'm not a big fan of in this problem is that they've mixed their notation in a funny way. I bring it up because I want you to know that it's an okay thing that they did it, but it's a little bit awkward. The other problem started I equal 1 as the lower value, right? And this one says n equal to 1, and they use n as their upper value, and our n is 140 here. And so the notation just feels a little bit funny, doesn't it? So be careful. The n in this problem is where I normally is. Okay, so the first thing to do then is to separate this out. This is n equal 1 to 140 of n squared minus the summation from n equal 1 to 140 of n. And then we're going to subtract off a1 and a2 and a3. Okay, so we'll go piece at a time. The n squared formula, take a look back at that. That one says we should have the upper value, which they were calling n in our problem. Upper value, that's 140, times what? 141 divided by, oh, I'm sorry, you're right, one more times. I was already thinking I was on the next piece. Times what? What's the last one? 281, yeah. And then divided by 6, right. All right, next piece. Summation from n equal 1 to 140 of n. 140 times 141 divided by 2. All right, A1. So remember, A1 means taking the original equation, or you can use this version of it where it's simplified by the distribution, and plug in the number 1. So what happens when you get the number 1 plugged in there? It's 0. Then we're going to take it and we're going to plug in the number 2. What does that give you? 2. And then we're going to take the a sub 3. We're going to plug in the number 3, and it's 6. So in the end, we're going to end up having to subtract 8 off. Okay, so grab your calculator, a little bit of multiplication, division, subtraction stuff going on here. we get a value? Sound good? Sounds good to me. Okay, so the next thing we're going to do is we're going to relate this into the calculus ideas that we have been doing, or we just started doing back in section 1. You guys ready? You guys all need to stand up and do some jumping jacks, I think. All right, area of a plane region. The area of this region, and by this region I mean from this value, we'll call it A, to this value B. So we're going to draw a line in here that marks it off. This is the area I'm talking about. All of this. The area of this region can be approximated by using rectangles. Okay, so what does that mean? Well, it means we can take this length and we can divide it into 2, and then into 4, and then into 6, and then into 8, however many lengths that we want to divide it into. And so picture-wise, I do a pretty good job dividing things into 4, so that's what we're doing is 4s. So if I were to divide this into rectangles, that wasn't good at all. Let me try that again. And they were all equal width. That's our goal, is to have equal widths of rectangles. We could find the area of the 4 rectangles, and we could add those areas together, and it would be an approximation for the area of the yellow shaded part that I just shaded. But the question is, how would I determine the height? I mean, the widths are determined. They're all the same. That's fine. Well, what do I do to determine the height? Well, there's 3 different ways. There's at least 3. We're going to talk about 3 different ways of determining the height. I'm going to do this approach, which is a rectangle approach. There is another approach called trapezoids. And so what you could actually do is you could actually use these corners. I'm just going to mention it so that if you ever see it again, you'll be like, oh, I remember the teacher talked about that. We didn't ever actually do one, but she talked about it. You could actually use trapezoids to catch this, and you can see that the trapezoids actually work really, really well on this curve in particular. Maybe not every curve, but for this particular curve, it would work really nicely. And that's a method that's been around for quite some time, but apparently not too long ago, somebody thought they discovered something new, and it was published, and people oohed and awed over it and super excited and everything, and then mathematicians looked at it and were like, it was a doctor, like a medical doctor, that discovered it. And mathematicians looked at it and were like, yeah, that was done a long time ago, just so you know. So we're going to do this using left endpoints. That's what we're going to do at first, okay? So I'd like for you to sketch in those same vertical bars. So you're on the next page. Those same vertical bars that I just did just a moment ago. And we will label the first point as x0, and the last one is x4. And we're going to subdivide into 4 rectangles in between. All right, so what we're going to do is we're going to use the left endpoint. So what does that mean? Well, here's x1. So let's look at x0 to x1. So if I go with this rectangle, the left-hand endpoint would be x0, right? I mean, correct? Not as in the directional right. Correct? So we're going to use this point. I'm going to exaggerate mine to make very clear. This is the point that's going to be the height of my rectangle. So I need a height of this, which means it's going to go straight across and down. It's a little bit not straight across, but you get the idea. That wasn't any better. That's the height of my rectangle. Obviously, it's an overestimate a little bit, right? I've included a little bit that's not really supposed to be included. Okay, we're going to do the same thing for the next set. So from x1 to x2, and if I use the left-hand endpoint at x1 and I make this over, I've got a even worse overestimate on this particular one, right? All right, x2 to x3. I'm going to use the left-hand endpoint, which is x2, and this one is a vast underestimate. Yeah? And then we're going to go from x3 to x4. So x3's height is right here, and then this one again is another even worse underestimate. But this is an estimate. We are going to find, in general, and we'll do one specifically in a minute, these 4 areas and add them together.
For x2 to x3, why didn't we do the same thing from x1 to x2?
We do the same thing. We just use the left-hand endpoint. Yeah, so we're not using the largest endpoint or the smallest endpoint. We're using the left-hand endpoint. There are ways that you can do that where you can look for the maximum point on the curve, between the two endpoints and use that one as your height as well. It's a little more difficult. The left-hand endpoint's easier to calculate than finding the maximum value between the two. Now, what did we actually do to find these areas? Well, there's 4 areas here, right? And how do we find the area of a rectangle? Length times width. So let's talk about the width of each of these things then. What is the width that's going on between each of these? Well, I've led you to believe, and I asked you to draw it in such a way that they were equally proportioned, right? So if we knew the width was the total of, say, like 10, and we had 4 rectangles, could we find the width of each rectangle? Sure, they would be 10 divided by 4. So whatever the width is divided by 4. For the sake of what I'm writing down right now, we're going to call this delta x. So this width right here is delta x. Just means change in x values, right? So the first rectangle is length times width. So this is, I'm going to call what I'm calculating L of x. I know L is a terrible letter to use because it looks like the number 1 when we write it sometimes, so make it scripty or something like that. I'm going to use L for left hand, okay? So the first rectangle is delta x, that's the width, times the height. What is the height of this rectangle? It's what? Okay, where was it determined? The left endpoint of this interval, which the left endpoint was at the value. Yeah, so, and I realize I don't have this labeled. This function is f of x. So yeah, this would be the height, which would be f of x0. So the height is the y value, right? F of x0. And the width is delta x. So that's rectangle number 1. Rectangle number 2, width, delta x. What's its height? F of x1. Width of the next rectangle, delta x. Height, f of x2. I've got one more rectangle to go. Width of the last rectangle, delta x. Height, f of x3. So notice there is no f of x4 in this list on this one because I never used that height over there at x4 for calculating anything. This is fine. There's nothing wrong with this formula. We're going to use this in every way, shape, or form. But I want you to see that this has a shorter way of writing it down. Do you see delta x in every single term? Well, why don't we just do the multiplication by delta x 1 time instead of 4 times? Instead, we could add up the f of x0, f of x1, f of x2, and f of x3 all together first, and then multiply by delta x. And then just for the sake of fun, I'm going to show you one more thing. What's that? That's exactly right. In fact, I'm kind of out of space here. Let me move this one down here. This can be written as the summation of f of x sub I from I equal 1 to, in our case, this is 4, but I'm going to write it as n because it could be however many n you have, times delta x. We wrote ours as I equals 0 on this one, and this would be n minus 1 because it's left endpoints. It depends on how you label them. If you label them differently, it would be different. I just chose to start at x0. If I had chose my labeling to start at x sub 1, because that was my arbitrary labeling. So I think when you see your book do it, that they're probably going to use the values as I equal 1 to n on that probably. Starting with 1 and ending with n plus 1 as their subscripts on their x values. Okay, this is left endpoints. But there's nothing special about left endpoints. I know you thought there were, but there's not. So we could also do this with right endpoints. So do the same diagram you did before. Draw those same vertical bars. And then we'll have the same delta x, right? All that's the same. But the heights are not determined the same way. So between x0 and x1, which height is it that we're going to be using? The right one. So that would be the height at x1 right here, correct? And then between, so this is the area of the first one right here. Definitely an underestimate, yeah? Second one, between x1 and x2, which one will determine the height? x2. And here's the height of this one. Or here's the area of this one. Between x2 and x3, x3 will determine my height. And here's the area of this one. Between x3 and x4, what will determine the height? x4. And this one ends up being a big overestimate now. It was a big underestimate before. Now, lest you think that it doesn't matter, this one feels like, this particular curve that I used for my example, feels like that the area is about as much overestimate as underestimate. And it kind of looks that way, doesn't it? I've overshaded and undershaded about the same amount on both of these drawings, actually. That happens sometimes. It really depends on what the curve is you're working with, because I could definitely give you a curve where that does not happen. It is always an overestimate, or it is always an underestimate, too. Okay? All right, so let's find out what is the area of this. Well, I know from the last slide that I don't want to multiply delta x out every single time, right? It's not helpful. So this is my r of x I'm going to call for the right-hand area. I know I want to multiply by the delta x at the end. What are my values that I'm adding together here then? What are the heights that I have? Let's start with the first rectangle. x1, right? F of x1. And we're going to add them up until we get to the f of x4. Right, Josh? Okay, does that make sense for everybody? Again, aside from labeling, this is the same summation formula that we had just a moment ago. So like the summation that we actually really have here, if we wanted to write it out, you can put the delta x either in front or behind it. It doesn't matter because it's just a constant value. But this is the summation. This particular one is a summation from I equal 1. I didn't write this on the other slide. This is a summation from I equal 1 to 4 of f of x sub I. The other one was the summation from I equal 0 to 3. I didn't write that one, but that's what this is, right? One more. We use the left endpoint, we use the right endpoint, and the last one that we're going to use is the midpoint. We're going to use the midpoint as the point where we take the height of the rectangle. Okay, draw your same 4 rectangles you had before. You can label them the same on the bottom as you did before. And this one, we're not going to create an equation at the end, expression for the sum. But what we are going to do is we want to sort of mark the midpoint of each of these, right? These midpoints are going to be the heights where we actually take the height, or the points where we actually take the height. So if you kind of trace this up here, this point right here, it's not a very good dotted line up, but imagine. That point right there is my height for my rectangle now. And this point about right here is the height for this rectangle. And this point right here is the height for this rectangle. And this point right here is the height for this rectangle. So you're using the midpoints instead of using the left endpoint or the right endpoint. And we have an example of just that. Now there's nothing special about using 4 rectangles. I like to use examples of 4 rectangles because they're easy for us to see, they're easy for us to draw, and dividing things into twice is easy to do. If you divide things into 6, that's a little trickier. Divide things into 7, it's almost impossible. Okay, just visually to see that happening unless you have very nice numbers or something to work with. So I like to divide things into 4. So some of your homework problems may have division by 4 like this, and some of them may not. They may be, dividing by 5 equal intervals. That's okay. It's just whatever you're working with, okay? Now, it's going to be extremely helpful whether you draw the whole picture or not to at least draw the number line of the subdivision, okay? So let me show you what I mean by that. This one tells us that we're going to use left endpoints, right endpoints, and midpoint values for the given number of rectangles to find 3 approximations of the area of the region between the graph of the function and the x-axis over the interval. So we have 4 rectangles we're drawing, and the interval is from 0 to 2. So what I'm really caring about you drawing, more for your sake really than mine, if I don't see it, it's not going to hurt my feelings. But you're going to help yourself out a lot if you simply draw the number line from 0 to 2. Okay? So you're thinking about starting at 0, you're ending at 2, and if you're dividing it into fourths, because it's supposed to be 4 rectangles, and you divide it in half, there's the number 1, and divide it in half again, and what are the other 2 values you get? 1/2, and what was that? 1.5. So you can either write that in decimal form like 0.5 and 1.5. You can write that in mixed number kind of form like 1/2 and then 1 and 1/2. Or you could write it as an improper fraction, 3/2. Whatever is fine. It doesn't really matter. They're all the same value. I think decimals kind of work nicely on this one, so I'm going to go with decimals. Okay, so far so good? It says we're going to do left endpoints, right endpoints, midpoints. So let's do the left endpoints first. So this will be L of x for the sake of differentiating between them. The first thing I need to know is I need to know the width of my rectangles. Well, if I've drawn the picture, finding the width of my rectangle should be easy. What is it here? It's 1/2, right? It's 0.5. The picture tells you what to do. Next thing, then, is to add up the function heights of each of the x values in question. This is left endpoint. So what is the first left endpoint? It's at 0 on this one, right? So the first left endpoint is this one right here. So it's 1, 2, 3, 4. These are my 4 left-hand endpoints that are underlined in blue right now. So I'm going to do f of 0, not 0, f of 0, plus f of 1, plus f of 2, plus f of 3. I think I left something off. I did. Hang on. I left a parenthesis out. There we go. Okay, I think I've got everything up there right now.
So, that's
Oh, I'm sorry. I was already thinking what I was doing next. You're right. No wonder you're looking at me like I'm crazy. How's that? Is that better? I think that's probably better. Thank you. We'll get that fixed. Okay, so f of 0, f of 0.5, f of 1, and f of 1.5, the first 4 values. Okay, what I was trying to focus on making sure that nobody did is actually add 0 plus 0.5 plus 1 plus 1.5 together. You need to add the function values of those values, sorry, not the x values themselves. How would I find f of 0? How would I find f of 1.5? What would I do? You can plug them into your calculator. Now this one's really nice because they all end up being nice, pretty values. They don't always do that. So I want to show you how to use your calculator to help you out to avoid rounding errors. Does that sound like a good thing to avoid? Okay. Grab your calculator, and I would like for you to put the original equation into your calculator. Okay, y equals, I want you to put in 2x squared plus 5 into y equals. Is it there? Okay, go back to the regular screen, not the graph, not the y equals, and the regular screen. Clear it out, make it blank, whatever y'all can do, okay? What we're going to do is we're going to type in a variation of what's on our screen right now. So I want you to type in 0.5, okay, and a parenthesis. The next thing you're going to do is you're going to pull up a button that we've used, but we haven't used it for a long time, so you may not remember where it is. We're going to put in y1. Does anybody remember where y1 is located? It's under a button called vars for variables. Okay, hit vars, arrow over to y vars. It's a function, y1. Okay, and then it'll put that back into your regular screen, just like it looks like on my screen on the board right now. And then you're going to put a parenthesis 0 plus. So no matter how ugly the value is at 0, which of course this one's not ugly, it's 5. I get it, right? But could it be an ugly number when you input a value into a function? Sure could. What if you're dealing with a square root here and you had square root of 5 as your first value? Yuck. Okay, so then you're going to do the same thing. You're going to do y1 of 0.5 plus y1 of 1 plus y1 of 1.5. And it's going to get awesomer. That's not a real word, but it is going to get awesomer in a minute here. So just hold tight. You're going to get an answer when you hit enter here. Hopefully everybody's answers match and match mine too. What do you get? What'd you get? 13.5 is what I have written down. Hannah, did you say you have 27? 20. See if Nate can fix it for you. What do you get, Evan? 19.
Mine says 615.
Did you guys put 2x squared plus 5 in your y equals menu? Oh, yeah, those parentheses matter. Okay. Oh, you pulled it back up here.
If I'm good at one thing, it's doing things wrong.
1 of 0. Hang on.